Amplifiers can be classified based on the frequency range of the signals they are designed to amplify. Different frequency ranges require different amplifier designs and characteristics. Here are some common classifications based on frequency range: audio amplifiers, low frequency, LF, amplifiers. These amplifiers are designed to amplify signals in the low frequency audio range, typically from 20 Hz to 20 kHz. They are commonly used in audio systems for music and speech reproduction. Radio frequency, RF, amplifiers, very high frequency, VHF, and ultra high frequency, UHF, amplifiers. These amplifiers operate in the VHF, 30 MHz to 300 MHz, and UHF, 300 MHz to 3 GHz, frequency bands, respectively. They are used in applications such as television broadcasting, two-way radios, and radar systems. Microwave amplifiers. These amplifiers operate in the microwave frequency range, typically above 3 GHz. They are used in applications like satellite communication, microwave ovens, and radar systems. Intermediate frequency, IF, amplifiers. IF amplifiers are commonly used in radios and communication receivers to amplify signals after the initial RF stage but before demodulation. The specific frequency range depends on the application but often falls in the hundreds of kilohertz to a few megahertz. Ultra-low frequency, ULF, and extremely low frequency, ELF, amplifiers. These amplifiers are designed for frequencies below the audio range, with ULF typically covering 0.3 Hz to 3 Hz and ELF covering 3 Hz to 30 Hz. They are used in specialized applications such as seismic monitoring and submarine communication. Broadband amplifiers. Broadband amplifiers cover a wide frequency range, often from DC, direct current, to gigahertz frequencies. They are used in various applications, including RF testing and broadband signal amplification. Optical amplifiers. Optical amplifiers are used in optical communication systems to amplify optical signals. They operate in the optical frequency range, typically in the infrared spectrum. IF to RF amplifiers. These amplifiers are designed to cover a wide range of frequencies from intermediate frequencies to radio frequencies, making them suitable for applications like frequency conversion in communication receivers. Subband amplifiers. Some amplifiers are designed to amplify specific subbands within a larger frequency range. For example, cellular communication systems may use subband amplifiers to amplify signals within specific frequency bands. Multiband and dual-band amplifiers. Multiband and dual-band amplifiers are capable of amplifying signals in multiple frequency bands simultaneously or switching between different frequency bands as needed. These are commonly used in modern communication systems that support multiple frequency bands. The choice of amplifier for a particular application depends on the frequency characteristics of the signals that need to be amplified. Amplifiers can be classified based on their transistor configuration, which describes how the transistor is connected in the circuit. Common transistor configurations include the common emitter, CE, amplifier, common collector, CC, amplifier, and common base, CB, amplifier. Each of these configurations has its own characteristics and is suited for specific applications. Common emitter, CE, amplifier. Transistor configuration. In a CE amplifier, the transistor's emitter terminal is common between the input and output circuits. Voltage gain. CE amplifiers offer relatively high voltage gain. Current gain. CE amplifiers provide current gain, but it is typically lower than the voltage gain. Input impedance. The input impedance is moderate, falling between that of the CC and CB configurations. Output impedance. The output impedance is moderate, making it suitable for driving moderate loads. Phase relationship. CE amplifiers typically invert the phase of the input signal, 180-degree phase shift. Applications. CE amplifiers are commonly used in audio amplifiers, where both voltage and current gain are needed. They are also used in RF amplifiers and general-purpose amplification circuits. Common collector, CC, amplifier. Transistor configuration. In a CC amplifier, the transistor's collector terminal is common between the input and output circuits. Voltage gain. CC amplifiers have a voltage gain slightly less than unity, less than 1. Current gain. CC amplifiers offer high current gain. Input impedance. The input impedance is relatively high, making them suitable for voltage buffering. Output impedance. The output impedance is low, which allows them to provide a low impedance output. Phase relationship. CC amplifiers do not invert the phase of the input signal, 0-degree phase shift. Applications. CC amplifiers, also known as emitter followers, are often used as voltage buffers between high impedance sources and low impedance loads. They are commonly found in signal buffering and impedance matching applications. Common base, CB, amplifier. Transistor configuration. In a CB amplifier, the transistor's base terminal is common between the input and output circuits. Voltage gain. CB amplifiers provide relatively low voltage gain. Current gain. CB amplifiers offer current gain, typically less than the current gain of CE amplifiers. Input impedance. The input impedance is low, making them suitable for driving low impedance sources. Output impedance. The output impedance is moderate, falling between that of CE and CC amplifiers. Phase relationship. CB amplifiers typically do not invert the phase of the input signal, 0-degree phase shift. Applications. CB amplifiers are not as common as CE and CC amplifiers. They are used in specific applications like impedance matching and RF amplification, where their input impedance characteristics are advantageous. Amplifiers can also be classified based on their amplification purpose, which relates to the type of signal they are designed to amplify and the specific characteristics they emphasize. Here are 3 common types based on amplification purpose. Voltage amplifiers. Amplification purpose. Voltage amplifiers are designed primarily to amplify voltage signals. They increase the amplitude of an input voltage while maintaining the same current level. Voltage gain. Voltage amplifiers typically have high voltage gain. Applications. Voltage amplifiers are commonly used in audio systems, communication circuits, and instrumentation. They are essential in applications where the voltage level of a signal needs to be increased without significantly altering the current. Current amplifiers. Amplification purpose. Current amplifiers focus on amplifying current signals while maintaining the same voltage level. Current gain. Current amplifiers provide high current gain. Applications. Current amplifiers are used in various applications, including sensor interfacing, photodetectors, and transimpedance amplifiers in optical communication. They are particularly useful when amplifying current signals generated by sensors or detectors. Power amplifiers. Amplification purpose. Power amplifiers are designed to amplify signals to deliver significant power to drive loads such as speakers, antennas, or motors. They emphasize amplifying both voltage and current to achieve high power output. Power gain. Power amplifiers have high power gain. Applications. Power amplifiers are used in audio amplification for loudspeakers, RF amplification for transmitters, and various industrial and automotive applications where high power signals are required. These 3 types of amplifiers serve different purposes and are designed with specific performance characteristics in mind. Amplifiers can also be classified based on the amplification devices they use. 3 common types of amplifiers based on amplification devices are transistor amplifiers, operational amplifiers, op-amps, and vacuum tube amplifiers, transistor amplifiers. Amplification device. Transistors, which can be either bipolar junction transistors, BJTs, or field effect transistors, FETs, are the primary amplifying devices in transistor amplifiers. Applications. Transistor amplifiers are widely used in a variety of electronic applications, including audio amplification, RF amplification, switching circuits, and digital logic circuits. They are known for their compact size, efficiency, and versatility. Operational amplifiers, op-amps. Amplification device. Op-amps are integrated circuit, IC, amplifiers that contain multiple transistors, resistors, and other components on a single chip. Applications. Op-amps are used in a vast range of analog and mixed signal circuits, including voltage amplification, signal conditioning, filtering, analog computation, and instrumentation. They are known for their high gain, high input impedance, and low output impedance. Vacuum tube amplifiers. Amplification device. Vacuum tubes, also known as electron tubes or thermionic valves, serve as the amplifying devices in vacuum tube amplifiers. Common types of vacuum tubes include triodes, tetrodes, and pentodes. Applications. Vacuum tube amplifiers were widely used in the past, especially in vintage audio equipment, guitar amplifiers, and early electronic computers. While less common today due to the prevalence of transistors and ICs, vacuum tube amplifiers are still favored by audiophiles and guitarists for their unique sound characteristics. Each type of amplifier has its own set of advantages and disadvantages, making them suitable for different applications and appealing to different preferences. Transistor amplifiers and op-amps are the most common and versatile amplification devices in modern electronics, whereas vacuum tube amplifiers are valued for their vintage aesthetics and warm, analog sound quality. The choice of amplifier type depends on factors such as the application requirements, desired performance characteristics, and historical or aesthetic considerations.